So I'm going to show a simple exercise that I think it's going to be a lot of fun. And we're going to do this in Grasshopper. So let me tell you first what I'm going to do. So we're going to build a surface out of triangles, but we're going to do it in Grasshopper so that we can actually twist it, right? So it's essentially, we're going to start as a flat surface, but then we look at how we can create parametric variations of it and control the angle of twisting. It's actually going to be like a helical form, and I think it's going to be very interesting. So let's get down to it. So first thing I'm going to do is create a row of points along the along the y-axis. So we're going to start with a series of points along the y, and I'm going to control the number of these points. Let's start with 20, and the spacing. So I'm just simply clicking on the canvas and putting in numbers, create number sliders. Okay, so these are the points. So the next thing is, actually, in order to be able to rotate this, we need to define the points in relationship to these points that we created. So these are going to be kind of the backbone of the rotation for this exercise. So in order to facilitate this, I'm going to create planes along these points, and then use those planes to create twisting geometry. So if you look at the coordinate system, this point array is aligned with the XZ axis. So I'm going to create XZ planes. And if you zoom in, you can see these are basically the plane orientations, and we have new coordinate systems along these points, right? So my X is pointing in this direction, Y is pointing upward. And if you want to create any point in relationship to these, you can use point oriented and then use these planes. And now those coordinate systems actually come in handy. So basically, let me actually make these a bit wider. So I'm going to go to plane size and make this 10. So we have larger planes. I can also increase the spacing a bit. There we go. So I want to create new points along the x-axis, right? So what I'm going to do is put, let's say, 15, and the u parameter is actually moving these points along the x. You can see it's moving along the red axis here, along these points, along the planes. And if I want to do, let's say, another coordinate, the v is actually moving it in the y direction, and w will move it in the z direction of the plane, but we're not going to do that now, so we're just going to use the u. And I'm going to put 20, and these are basically the new points. So let's draw a line, and I'm going to make actually a copy of this point oriented and delete this. You can also deconstruct these planes to extract the points, but essentially we are just building profiles using C-planes, right? So these are construction planes that we can use. Okay, next up is we create lines going from these points to these points. And actually, this is where it can get very interesting. So how do we model the surface, essentially, right? So what I want to do is connect these points or these lines as like a strip that we can also twist later on. So in order to do that, we need to kind of loft these surfaces. So let me show you. If I were to loft these, this is essentially the surface we want to build. But if we were to twist it, then it can create non-flat construction geometry. So these might start distorting a bit because of the loft operation. So instead of doing loft, I'm actually going to do triangles. So how do we build the triangles? So one way of thinking about this exercise would be, how do we connect these lines, right? So let me actually bake it first. And then let's look at these two lines here. So how do we connect them? If I grab this line and do extrude curved point and extrude it to this base here, and then do the same for this line but go in the opposite direction, this will be the kind of triangular construction that I'm aiming for, right? But we need to do it in an almost like an array way, so we can do it, let's say 20 times. So this is, let's see, array x, and this will be 20, and this is 1. All right, so this is actually the surface construction I'm aiming, minus the last one. So how do we build this type of triangulation? Well, we need to filter some of this data that you see here. So these lines, we need to organize them in a way. So what I need to do is I need to get, look at the number of lines. I have 20. So we can do point on curve to look at the list, see how it's organized. So I'm grabbing just one point along the curve and then do point list. And here, let's put 5. So there we go. So we start from 0 and go all the way up to 19. So what do I need? I need a list that goes from 0 to 18. And then I need those lines to connect to another list that goes from 1 to 19, right? So I'm kind of shifting the data into two lists so that we can create connections between them. So I'm going to move it out and then do a shift list here and grab this line. And in order to shift the list in the negative direction, I need to get rid of 19. So I supply -1 as the shift index. And then I need to turn off the wrapping, because what wrapping does is if you wrap it in the negative direction and keep it on, you can see that the list actually shifts, but it maintains this last item here and it becomes the first item in the list, right? So it's kind of shifting data in the negative direction while keeping the same elements. But what we want to do is turn the wrapping off, and you can see now this last line has been eliminated, right? So it's taken off the list. So these are the lines that I want to extrude to these corner points here. So how do we find those corner points? Well, there are a bunch of ways we can do that too. So you can see we have the endpoints here. We can also do a shift list to these points. So I can simply make a copy of the shift list, but this time I want to get rid of the first point in this list, right? So if you look at this point list, let's say we grab these points here, and then this is their ordering. So what I need is this list to not start from 0, but start from 1. So in this case, the shift will have to be positive. So I start from the second line and go all the way to the end. So there's also another reason to check for this connection. So we have 19 curves here and 19 points, right? So the data has to match 1 to 1. So if I do extrude the point and grab these lines and extrude them to these points, that's basically half of my construction, right? So that's what we intended to do here. So I'm connecting it to this base. Now we can actually do the same thing in the opposite direction, right? How do we do that? Well, we make a copy of the line list, but rather than shifting it from the end of the list, now I'm going to shift it from the beginning of the list, right? So I'm going to switch this to +1. So I end up with a list like this. And let's look at our points. This time we're going to connect them to these points here. So for that, I need to use this list, and they have to be shifted in the negative direction. So there is some form of symmetry in this sort of operation, right? So this edge kind of goes to this point, as if we are like doing in reverse, but actually not. So we start, this list data still matches 1 to 1. So if you look at the output, this is 19 curves and these are 19 points. So if I copy paste this, plug them here, these are the other halves of my construction. So let's put them here as my surface output. And that's essentially it, right? It's a very basic construction, But because we built it using planes, now we get to do a lot of cool things with it. So now we can actually start twisting or morphing these surfaces or surface construction. So let's look at how we can do that. Well, the planes are here, right? So if I use rotate plane, which basically rotates the plane using a degree, but it rotates it along its z-axis. So I can just get this plane, and then let's do 0 to 360 just to see how we rotate this. And I right click here and do degrees for rotation. And this will be my rotated plane. So let's look at it here. You can see the planes are rotating clockwise, clockwise to our view. And they're also, I think, compared to the right-hand rule, they're also rotating counterclockwise. But according to the z direction, it's rotating counterclockwise for the plane, but it's rotating right side to my view. So if I plug this in, remember that we made our point construction oriented to planes, right? So now if those planes are rotated, our planes are going to be rotated as well, right? So that's basically that whole thing can be controlled by rotating planes. But my intention is to do something a bit different. I'm not trying to rotate all the planes the same degrees, but I want to rotate them gradually, right? So I want to give it a twist. What if the rotation for the first plane is 0, while the rotation for the last plane is 360 degrees, right? So it's going to create kind of like a helix using this point construction, or this end point, as kind of the axis of rotation. So let's look at that, how we can do something like that. I'm going to go here, and we have our plane, and we have our plane rotation. For this operation, I'm going to use something called Graph Mapper, a very easy, intuitive, and kind of continuous transformation tool. So we can attach a range to it, and we can actually first learn about how this works. So if you right-click the Graph Mapper, select the graph type, let's start with linear. This is like a mathematical function. So we supply a value in the horizontal direction, so the graph goes from 0 to 1, and it gives us an intersection with the graph in the vertical direction, which is, again, 0.0 to 1. So if I were to give it 0.5, you can see we get this sort of red line forming. That's kind of where we evaluate the graph. And that will give me an output that corresponds with the graph. Now, since this graph is x equals y, or it's going basically diagonally, it's giving me the same value. But if I move this around, you can see I'm actually changing where it intersects with the y-axis, right? So if I move it along the graph, I get different values. And that basically can be utilized to make continuous transformations. So how many rotations do we need? Well, we can actually look into this a bit later, so I'm going to move it down. Let's say that we create another series here. So I'm just going to copy it. And for this one, let's keep this as our rotation value, right? So let's say we want to rotate 20 planes by 5 degrees each. And so this will give me 0 to 95 rotation. So if I replace this here, you can see I'm actually getting a serial rotation. I can also increase this, and you can see I'm just increasing the rotation angle, right? And that's actually what I wanted to do. So that's kind of the twist we want to generate. Okay, so how do we use the graph mapper now? Basically, rather than using a series of values, we can attach a range function here that will divide the x domain from 0 to 1 into equal increments, and we can use the graph function to control rotation. So for that, I attach a range here, and if I supply 20 to this, it will actually divide the interval, which is 0 to 1, into 20 equal segments, but it will give me 21 values of evaluation. So we need this to correspond with the number of planes we have, and that's why I'm going to right-click here, write a small expression, and call it x minus 1, so that if this is 20, we supply 19 here, but we get 20 values. And I'm going to combine it here and use this as a coefficient now, right? So we have 20 values. If I were to supply this as rotation, that won't be enough. So instead, I'm going to just multiply it with the amount of rotation I want. So what if we want the maximum rotation to be 360? So that will basically multiply all these values and give me that value. We can actually keep it as a diagonal line. This is my rotation, and I'm going to supply it here, and voila. So what's happening is we start with 0-degree rotation for the first line, but then we have incremental steps, and it ends at 360 degrees, right? So the last line makes a full circle, actually. And if I increase this number, it will just extend the rotation. And if I reduce this, that will also compress the element. But this increment actually doesn't change the rotation because the range kind of fixes the total number of rotation, right? So we are getting these as kind of coefficients like percentages, and this is the total amount of rotation. I have to change this to be able to rotate it multiple degrees. So I would recommend to do multiplications of 90 so that these surfaces can combine later on. But I'm going to keep it at 360. And let's see what kind of surfaces we can generate. So I'm going to delete, or we can keep this as well. It's like our initial surface construction. And then let's come back here. We used 30 here. Let's make this a bit less. Let's keep it 20 and make it longer. So I'm going to keep it at 6. All right, so let's bake a few surfaces. So I'm going to bake this one, move it aside, group it. We can also bake one that goes to 90, right? Something that twists like this. And if you want to control, let's say, this curvature, you can also change this graph type to be conic. So that will also give me different types of interpolation. So if I move it, let's say, bulge it a bit in this direction, it will basically start rotating a lot early on, but then it will kind of rotate less towards the end, right? So this kind of controls the amount of rotation per section. So I'm going to keep it somewhere here. Take this one. So let's bake a bunch of these. Let's change our graph type and then change this to 180. Bake this one as well. So you can see it basically becomes a tool that can output a lot of dynamic surfaces, but the surface information is continuously constructed because of my triangulation. So I'm going to go back to the linear one. And if you change this by any chance, this might actually end up not fitting to the angle you want, right? So it's because I want the full rotation and I want this to control the full rotation. So this basically dictates the angle of rotation for me. So I'm going to do one more, which is 270. And let's make one more, which is going to be just 0. So it's basically flat. So I end up with 5 different unique surfaces. Right, so this can output unlimited numbers of variation, but essentially I'm constructing them in a continuous manner, and I can use these to make other types of dynamic connections. So I would just group these And you can look into making some meaningful connections. For instance, this can go here. Some of them can rotate. Maybe this goes here, so they can actually merge. Where shall we put this one? So this can go, let's see, this is kind of closed. We might have to put it somewhere here, actually. You can also rotate it. We can also mirror it. Does it help when we mirror it? Well, maybe we have to rotate it like this. If I put it here, these two start intersecting. So maybe we have to shift this one in another direction. Maybe make it vertical. That's going up. So if I were to put this down, they might start intersecting as well. I'm just trying to build this type of dynamic shape without kind of intersecting these surfaces. So that seems to be the right way. And this one, I'm just going to place it here. There we go. So it's basically gave me a very interesting kind of structural surfaces that we can build out of planar faces. And we can actually do a lot more with this, right? So you can take it, mirror it if you want to start stacking them up. Maybe this goes in the other direction. What if I put this here? There you go. It's already starting to get very interesting, very dynamic. And I'm actually using the kind of symmetrical pieces, connections between these surfaces to kind of build complex networks, right? And for that, I'm using kind of the mirroring operations, rotations, and kind of looking for how they could join in 3D. And also this type of linear construction helps to orient how we can join them. And they can always be taken out or removed or plugged in elsewhere, right? That's always a possibility. You can also change, let's say, like these two can be deleted. So we end up with something like this. So give it a try, and I think this could be a very interesting exercise that combines parametric modeling, a tool like Grasshopper, and then building these like continuous morphing surfaces, and then how you can stack and combine them to define structural networks between these surfaces. Okay, so experiment with this. I think it's a very simple tool that you can use. Only a few tricks, like as long as you build your constructions on planes, then you can control the rotations of the planes using GraphMapper or some serial numbering, and that will give you always the right type of construction. And you can actually control the amount of rotation, the amount of panels, and how you want to basically abstract these surfaces. Okay, so I hope you enjoyed this tutorial, and if you have any questions, let me know in the comments below. Otherwise, I'll see you in the next tutorial. Take care.